Mr. Butterworth, what an appropriate day to be working on this because it is raining out and we're looking at Blame It on the Rain.
I mean, it's not raining out here yet, but it's supposed to later.
It is, and it's supposed to rain quite a bit from what I saw on the radar.
That is true. My wife's going to spend some time outside today, and she's going to get cold.
That's exciting. Being cold is so much fun. Okay, so this is about what we call modeling with functions. This is one of the big things that we do with math, potentially as a career. We try to create math to help us understand how the world around us works and make predictions about things. And this activity is going to start off by looking at some drains, but we got some warm-up stuff going on here. I'm trying to use this table to make some kind of a function here. I'm going to try to see what I can do with this. The first thing I notice is that it doesn't appear to be linear. And
whoa.
oh,
I think it does because they're messing with you because I'm seeing the y
yeah.
from -5 to -4 go down by 2. So I like that. That's down by 2 and that's down, I mean, up by 1. But then we go up by 4. I'm hoping this is 8. Is that 8?
It
Yeah, that's
is.
down
Okay.
by 8. So it is a linear move. Oh, we wrote 8 at the same time. It is a linear move, but the table is a little trickier.
And then we're going up by 4 again, and we're going down by 8 again. So we're saying that this is linear because the change in y compared to the change in x is the same each time.
Yes, and so the slope for every 1 we go over on the x, we go 2 down. So the slope's got to be -2 over 1.
I also noticed that we are given a y-intercept.
Ooh, I like it.
That's really nice for a linear equation. So I could make an equation that looks something like f of x is equal to, we said the slope was -2 over 1. What if I had said -8 over 4? Would that have been okay?
Well, 8 divided by 4 is 2, so yes.
Okay. And then we've got x and plus 14 to do the form that our students love, which is their friend y equals mx plus b.
Now, they may also know some other form, so I'm going to write one other form.
Ooh, I like it.
So I'm going to pick this point, -422, and I'm going to write it in point slope form. Y minus 22. We still have the same slope. Then x minus -4.
Could we have done the same thing with the point like 5, 4 and said y minus 4 is equal to -2 over 1, x minus 5?
We certainly could have.
Cool. So it sounds like point slope form, which is what this one is really helpful if we don't have an easy point for the y-intercept.
That is true. And if you think of the transformations we did with putting quadratics in vertex form, there's some connections there.
Oh, yeah, this kind of looks like vertex form, but without a squared thing. So it's a line and not a parabola.
It does. And if we moved, that's interesting. I can't see yours on my screen. If we moved your 4 over, you can make it look much more like vertex form.
I think you're writing right now, but I don't see anything.
I didn't write anything because I realized that what I was writing and what you were writing was not in the same.
Fair enough. Cool. I like it. Okay, so we're starting with this idea of a drain thing. And they're looking at the storm drain, which lets extra water that's pooling in areas kind of run away from streets and run away from places that we as humans need to use. So we have a rectangular shaped metal drain. This is a rectangular prism, and it's kind of folded up so that we get this area that water can run through. Since we're not in person, we can't really compare your drain to other classmates' drains. But why don't you take a couple sheets of paper, pause it for a second, and see if you can come up with a couple different ways you can fold paper in this way to make this type of a drain.
You're saying they should take like a rectangular piece of paper
Mm-hmm.
and they should fold up the sides of it and see the different shapes that they could make. I
Yeah.
mean, they'll all be the same shape, but see the different things going on with the shapes.
Sure. Okay, hopefully you've paused and tried that. You might end up with some shapes that are like this, or some that are like this, maybe some that are a little bit more balanced like this. And you might be able to answer some of these questions based on that.
So how does folding the sides of the drain affect the bottom width of the drain? Is it fair to say that the higher the sides, the skinnier the bottom?
So the higher the sides, the skinnier the bottom. I like it. That looks pretty true for me.
And then in terms of describing the drain, we think best fits the needs of the town. It's going to have to be tall enough to like contain the water, but not so tall that it will block the water. Is that fair to say?
I think so. So would it be fair to say that when you're saying contain the water, you're talking about lots of volume?
Yeah.
So it's fun because both Mr. Butterworth and I teach calculus, and this is quickly approaching if we want to ask a specific question about this, a calculus type problem. This is actually something called volumetric flow, and Mr. Butterworth knew that I wouldn't be able to resist saying that word because we're trying to figure out how to get the most water through this drain without either taking up too much room or without causing the water to kind of stop up.
Yeah, and they comment there, it's got to be wide enough so it doesn't get plugged. So much like your gutter,
Mm.
you want your gutter to be a good size so that it doesn't get plugged up. It's going to get plugged up anyway. You got to empty the leaves out, especially right now because the leaves are falling. But you want to make sure that you have it wide enough so it's useful, but not so wide that the height no longer is helpful.
By the way, gutters are things on the outside of your house along the roof inclines to collect water and take it away from the wood of your house.
That's true. And newer houses have those. Some of us who live in older houses, those do not exist.
Wouldn't let me change page.
I was like, this is an awkward pause. That's fine.
All right. I'm going to kind of hide the ask yourself a little bit. So we've got sheets of metal that are 8.5 feet wide. Hey, paper that's standard size in the US is 8.5 inches wide. I wonder if that number was chosen for that reason.
I bet it was.
So that people might be able to kind of fill in this table by measuring things with paper. That's pretty cool. So the engineer wants to identify possible heights and bottom widths that she could use to construct this. Cool, I'm going to do the bottom one. So if the height, that's going to be, leave me with negative.
So it's 5, but that's 5 on each side, right? So that's 10 overall.
Yep.
So that means if you use 10, you've got to pay back 1.5, right?
It's
So
true.
that they're saying negative.
It is.
You seem to be having issue with your Apple Pencil being dead. I got you.
am.
So negative 1.5 for that. You just talk. All right. Don't worry.
Cool.
So a
That's
key
why I
part
wouldn't
there
do anything.
yeah. A key part there is double the 5. That's 10. And we only have 8.5. So if we've already used 10, negative 1.5 would be the bottom width. Obviously, that makes no sense in the context of this problem.
I agree.
So another one is 3. Double that is 6. And then we have 2.5 left for the width. 1.5 doubled is 3. So then we have 5.5 left for the width.
I'm just going to show what this one would look like just because I like that. So this would be 3 on the side, 3 on the side, 2.5 on the bottom.
And it looks like they want us to fill in some other numbers. So I'm going to go ahead and fill in a couple of heights that might make some sense based on what they're telling us. It's interesting that they kind of gave us spaces for going by 0.5s until we get to 3.
That is interesting. I'm going to do the calculation for 4 because that would give us 0.5 of a height. So I'm wondering if they kind of wanted to lead us down the path and say that that might be a little bit too thin in terms of the height.
So if it's 0.5, that's 1 that I use, so 7.5 is left. If it's 2, that's 2, so it's, oh, is this just going by ones now? So is that going to be 4.5 and 3.5?
Oh, that's interesting. Yeah, it looks like it. So every 0.5 of the drain that we're going up, we're making the width smaller by 1, which also makes sense because you're doing 2 heights and only 1 width. So it's like you're doubling the 0.5 to get the change of 1.
So is this the same? If I go from 0 to 1, I go down by 2 on this side. If I go from 1 to 2, I go down by 2 on this side. Is this the same slope as the original problem?
It is.
That warm-up?
Yeah.
So determine a function w of h for the bottom width given a height of h feet.
So we said that it was going down 2 for every 1, so that'd be a slope of -2.
Yeah, which we already did because we multiplied the height by 2, right?
Yep.
So really what we did, which might make more sense, is we took the 8.5, subtracted the height, doubled.
I actually prefer this way as a way to write slope-intercept form as a b plus mx, because you have a starting point plus or minus a change, and I really like that.
And you've mentioned calculus, and in calculus land, it helps us also.
In statistics as well, this is how we write linear equations in statistics.
Yeah.
All right. So now we have some more calculations to do. So we're trying to let the most water through the drain. We kind of teased this by suggesting that this was about volume because that's the most water. And since we don't know how long this drain is, all we can think about is they have a picture here where they show a slice of the drain, and the cross-sectional area is going to be the way that we figure out how much volume of water can flow through this drain. That kind of answers question 2 as we in words without necessarily having any numbers to go with that.
So the engineer needs to calculate the cross-sectional area.
Yeah.
Got it. And to calculate that area, that's just a rectangle, right?
It is.
So don't I just multiply the height and the width?
You do. I just want to write that there. Just for some reason, I don't really know why. Oh, we might need it for any drain, so we don't have, oh, so I did write it for a reason. I like it.
See, I got confused because I said you had to multiply W and H, the width and the height, and then you wrote W of H.
Yeah.
So that's an unfortunate choice of lettering.
It is.
But that's okay. But maybe they did that on purpose. We'll figure it out. So the bottom width is really this. And then the height is just H, right?
So are you saying that if we did the bottom width, which is 8.5 minus 2h, multiplied by the height, which is just h, that would give us that cross-sectional area?
Yeah, because you just do the width times the height, and the width we wrote is that expression on the previous page.
Cool. I like it.
Predict and describe the drain with the maximum cross-sectional area. I like squares.
I do too, or squarish things.
But wait, wait. That's like in factored form, right?
Oh, it is, because we have two
So
things.
if I'm seeing that maximum word, that makes me think of the vertex, right?
It does, because we know that anytime we're talking about a max or a min with things that have two things being multiplied that give us a parabola, that's the vertex.
So my prediction is going to be halfway in between whatever the zeros of this is. And we can find those zeros. The zero for this one is easy. That's 0.
I was going to find that one.
Oh, well,
all right, I'll find that
one.
So the 0 for this one is when 8.5 minus 2h is equal to 0. And that means that that's when 2h is equal to 8.5. So h equals 4.25.
So then we got to find the middle of those two. So that's going to be like 2 and a little bit.
So if I were to begin graphing this, we're talking about here at 0,
Mm-hmm.
here at 4.25, and then exactly between those, we've got 2 and a little bit, as you said, 2.125, which would be where that max occurs.
And then we know this is going to be a down parabola. So it's got to look something like this.
And that's because we have a negative h that's going to, if you multiply it out.
Yeah, if we use the distributive property to multiply the h, we get 8.5h minus 2h squared. And the minus 2 means we'll be concave down. You could also just plug the 8.5 minus 2h times h into Desmos and look at what the picture looks like if you don't believe us.
It's true. Okay, so we answered question 5 over there, so I just rewrote that up there.
That's because we were supposed to describe. So our description should have been, we multiply the width and the height of the figure there. And then our actual function is what we wrote.
And now we've kind of predicted and described. We haven't actually calculated that, and that's okay because we're not asked to. Don't forget to label our axes. We haven't done that yet.
Ooh.
So this would be, nope, height. And then we said this is maximum area.
So that's area, which they're calling A of H.
I just called A.
And there is a T on the height. Don't worry, Mr. Carlson does know how to spell. He is not a horse.
Oh, it didn't show up on yours, huh?
No, it looks like nay.
There we go.
But I know it said height. What is the maximum cross-sectional area for the drain pipe? Well, we found out where the max was. That was that 2 and a bit, that 2.125. So we just plug in 2.125. Again, you could also use Desmos to help you out.
And when we do that, we get 4.5 times 2.125, which is going to be somewhere around 10-ish.
So we're going to let them actually calculate that. Identify and label the intercepts of A and H on your graph. Okay, we already did that on the previous page. That was the 0 and the 4.25.
Yep. We didn't talk about
what the number was.
Yeah, we didn't talk about the meaning of those things.
Right.
The meaning of those, so those are both places where this problem stops making sense. So if you do height of 0, you don't really have a drain. And if you do a height of 4.25, you basically get a piece of metal folded in half because there's no space left for the bottom.
Which would also be totally useless.
Axis of symmetry, we kind of did that. We didn't explicitly state that that was, I guess we're talking about an h-axis. H equals 2.125.
I like that you made the mistake of writing x, though, because that's helpful for the students to remember that often we call that x, and the axis of symmetry has to be an x equals equation.
It's true. And if you're in Desmos, you really should be using x. I learned yesterday that you can use other letters if you're careful, but you have to stop it from trying to make it equal to a number, which a number of my friends did not do when they were using it on their spiral.
I think if you wrote A of H like you have up there, I think that would work on Desmos.
Even y equals that will come out okay. Describe the relationship between the axis of symmetry and the maximum cross-sectional area. The axis of symmetry is the value of the height that that max occurs at, which we've talked a lot about, the vertex and the axis of symmetry going together. So hopefully that's kind of beginning to stick a little bit. Ooh, now I have to draw and label a drain with the greatest cross-sectional area. I like it.
I drew a drain.
All right, I'm going to say this is 4.25. Nope, I lied.
Wasn't that 2.125?
Yeah, I just tried to double click my pen to get it to turn to an eraser. It was confused why it didn't. 2.125.
And then this side's also 2.125 because they have to be the same.
And then we've got, we don't have 4.5 on the bottom, we have 4 on the bottom.
Gosh, Mr. Carlson, goodness.
Nope, I lied. I have to erase stuff again.
4.25, right?
There we go. 4.25 on the bottom.
So to label, what do you think they want us to do for the labeling?
Probably, I'd say at least units. I think we're in feet.
And maybe say like, this is the width. And this is the height.
That could make sense.
And then I'm looking at that. Think about, is there a way to determine the maximum cross-sectional area using the x-intercepts? That's kind of what we did.
Yeah, it's definitely what we did.
So we used the x-intercepts to then find where the vertex was and went from there.
I'm wondering if the intent or the expectation of the problem was to multiply that out and use the negative b over 2a thing.
It could be, but that sounds a lot more confusing.
Yeah, that's way more complicated.
Hey, that's what we built. Identify the first factor and its function family. H.
Okay. So it's breaking this up into its factored form like we did.
What do they mean by its function family?
Well, we've talked about 3 function families so far. We've talked about linear functions and quadratic functions and exponential functions.
Oh, and those are called families.
They are.
Got it.
I'm going to identify this as linear, and I can do this kind of by elimination. I don't have a variable and an exponent, so it's not exponential. I don't have the variable squared, so it's not quadratic. And I know my linear functions are something just times a variable, and here we have 1 times h.
So is it fair to say for the second thing, it's 8.5 minus 2h, and that's also linear?
I agree.
For the same general arguments that you just said?
And we also talked about this a lot as the slope of -2. So that kind of helps us see that as well.
What would the slope of yours be?
Slope would be 1.
Okay, so if there's nothing there, I can put a 1 there.
Yes.
And then to describe what it represents in terms of this problem situation, that's the height.
Mm-hmm.
And then in part B, that's the width.
I like it.
Width. Then it asks us, identify the type of function created by the product. Well,
So
we've already talked about that. That's got to be quadratic, right? That's what
Yep.
we've been talking about.
So if you multiply 2 lines together, you get a quadratic function.
But why does this happen?
Algebraically, it happens because we're taking a linear variable, so a power of 1, multiplying it by another one that has a power of 1. If you have like x times x, or in this case, h times h, that gives you an h squared. And we know that squared things are quadratic, which is why we call them quadratics, because it comes from the Latin to mean to square something.
Got to go with those word roots that Mr. Carlson knows. All right, so now they walk us through this modeling process. So we've got a notice and wonder where we gather information. I like that it says notice patterns. I love noticing patterns.
Mm.
And maybe that's why they started us this year with patterns. So we could start thinking about patterns.
I think it is.
Formulate some questions, organize and mathematize. That's fun.
That's a fun word, yeah.
Predict and analyze, and test and interpret. Is this like kind of related to the scientific method?
A little bit. It's slightly different than the scientific method in terms of you're not necessarily trying to understand why something happens or make non-mathematical predictions based on observations.
Got it.
So I feel like this is something that mathematicians do a lot, or engineers do a lot, or scientists do a lot in terms of trying to use math. Ooh, so now we've got kind of describing these modeling steps in terms of this activity. I think this is a great thing to make a journal, like it suggests in the bottom corner of this.
That does sound great. So what we would like you to do is think about what we did, and we'll put that as part of your journal prompt. And you can write down some of the things that you're noticing. And that you can either think of how you might have thought about it, or you can think of how Mr. Carlson and I thought about it, if you need some support there.
Either one of those is okay.
And that's it. Now it's up to them for more talk the talk and such like that. So if you're confused on how to kind of start this process, think about what we did and think about how it relates to this different, slightly different situation.